Welcome to this lecture of calculus. In this lecture, we shall study the proof of the Cauchy's mean value theorem and discuss few of its examples. First, we see what is the statement of the Cauchy's mean value theorem. The Cauchy's mean value theorem states that the two functions f and g be continuous on the closed interval a comma b. Second, differentiable in the open interval a comma b. And third condition is g dash of x is not equal to 0 for all x belonging to the open interval a comma b. Then there exists at least one point c belonging to the open interval a comma b such that f dash of c divided by g dash of c is equal to f of b minus f of a divided by g of b minus g of a. So this is the statement of the Cauchy's mean value theorem. Now let's take up its proof. For the proof of the theorem, we must first of all notice that we have g of b minus g of a in the denominator of the Cauchy's mean value theorem. So therefore, the conclusion of the Cauchy's mean value theorem must be valid provided g of b minus g of a is not equal to 0. So therefore, it is valid provided g of b is not equal to g of a. Now let's first see how this is true automatically under these conditions that g of b is not equal to g of a. Now first of all, notice that so we note that g dash of x is not equal to 0 for all x belonging to the open interval a comma b. Now let's try to look at the function g of x in terms of the Rolle's theorem. So the first condition of the Rolle's theorem is for the function g of x. So we have g of x is continuous. That is the first condition of Rolle's theorem. Second, g of x is differentiable. That is the second condition of Rolle's theorem. And if the third condition of the Rolle's theorem is true, that is if g of a is equal to g of b. Suppose if this condition is also true, g of a equals g of b, then Rolle's theorem concludes, then Rolle's theorem guarantees g dash of, suppose say some number c is equal to 0 for some c belonging to the open interval ab. So here we are writing this thing. We are already given that g of x is continuous, g of x is differentiable. Now suppose if g of a is equal to g of b, then Rolle's theorem will guarantee the existence of a point c such that g dash of c is equal to 0. Now here comes our valid point. We are given that g dash of x is not equal to 0. So we are given g dash of x is not equal to 0. Therefore, therefore the third condition of the Rolle's theorem cannot be true for the function g of x, because otherwise we will definitely have a point c belonging to the open interval ab such that g dash of c is equal to 0. But that is not true, and it's already excluded from the statement of the Cauchy's mean value theorem. Now suppose if possible, if g of a is equal to g of b, then all conditions of Rolle's theorem are true, are satisfied. So there exists at least one point c belonging to the open interval ab such that g dash of c is equal to 0. But this is a contradiction, which is a contradiction, because we are given that because g dash of x is given to be non-zero for all x belonging to the open interval a comma b. So therefore the third condition of the Rolle's theorem cannot be true for the function g of x. Now let's define one function here. So now define a function, say h of x which is defined as f of x minus f of b minus f of a divided by g of b minus g of a into g of x. So this is how we define the auxiliary function for proving the Cauchy's mean value theorem. So again, clearly h of x is continuous on the closed interval a comma b, differentiable on the open interval a comma b. This is true because we have the function f of x is continuous as well as differentiable, and g of x is also continuous as well as differentiable. Now let's evaluate what is the value of h of a and h of b. In fact, we shall try to prove that h of a is equal to h of b so that all the three conditions are of the Rolle's theorem are satisfied by the function g of x, and then we can conclude the proof using Rolle's theorem. Now let's evaluate h of a minus h of b. Now h of a minus h of b, this is equal to f of a minus, let's write this as some like k times g of a, whereas k is this number f of b minus f of a divided by g of b minus g of a, then minus this is f of b minus k times g of b, where we have simplified our notation, where this number k, this is equal to f of b minus f of a divided by g of b minus g of a. This is just to simplify our writing here, otherwise this is not necessary. Now we can write this is equal to f of a minus f of b, then minus k times g of a minus g of b. Now at this stage we shall again replace the value of k here. So this is equal to f of a minus f of b minus. Now the value for k is f of b minus f of a divided by g of b minus g of a. Now this is multiplied by g of a minus g of b. Now we can clearly see we can cancel out this g of b minus g of a, and this minus becomes plus, and then finally we get f of a minus f of a is cancelled, and f of b and positive f of b is also cancelled, so this whole thing becomes 0. Therefore we have seen that h of a minus h of b is equal to 0. So therefore we conclude, so hence h of a is equal to h of b. Thus, the function h of x satisfies all the three conditions of Rolle's theorem. Therefore, there exists a point C belonging to the open interval a comma b such that h dash of c is equal to 0. Now let's evaluate what is this h dash of c. So now h dash of x, this is equal to f dash of x minus f of b minus f of a divided by g of b minus g of a into g dash of x. So this gives, now substituting c equal to x, we get f dash of c minus f of b minus f of a divided by g of b minus g of a into g dash of c. This is equal to 0. So this implies, now dividing by g dash of c, we get this f dash of c divided by g dash of c. Now transferring this negative part on the right hand side, we get this is equal to f of b minus f of a divided by g of b minus g of a. So we conclude the proof of Cauchy's mean value theorem. Now let's take an example. This is verify Cauchy's mean value theorem for the functions f of x is equal to x square and g of x is equal to x cube on the closed interval 1, 2. So in the solution, so given f of x is equal to x square and g of x is equal to x cube on 1, 2. So clearly both f of x and g of x are continuous on the closed interval 1, 2 and differentiable in the open interval 1, 2. Moreover, we must also verify that g of 1 is not equal to g of 2, that is g is not equal to 0 anywhere, that is the derivative of g is not equal to 0 anywhere in the open interval 1, 2. So moreover, g dash of x is equal to 3x squared, which is not equal to 0 for all x belonging to the open interval 1, 2. In fact, we can see that g dash of x equal to 3x squared. It is equal to 0 provided x is equal to 0. But 0 does not belong to the interval 1, 2. Therefore, g dash of x is not equal to 0 anywhere. So hence by Cauchy's mean value theorem, there exists a point C belonging to the open interval 1, 2 such that f dash of C divided by g dash of C, this is equal to f of 2 minus f of 1 divided by g of 2 minus g of 1. Now we can see that f of 2 that's equal to 2 square, f of 1 is equal to 1 square because f of x is equal to x square, and similarly g of x is x cube, so g of 2 is equal to 2 cube, g of 1 is equal to 1 cube. So we can see this is equal to 3 divided by 7. Now this further gives, so this implies now f dash of c, since f of x is equal to x square, so f dash of c is equal to 2c. G dash of x is 3x square, so g dash of c is equal to 3c square. So therefore this is equal to 3 divided by 7. So now this implies 2 divided by 3c is equal to 3 divided by 7. So this implies c is equal to 14 divided by 9. And we can see 14 divided by 9 is equal to 1.55. So which is clearly a point which belongs to the open interval 1, 2. So therefore we have found a value of c which is equal to 1.55, which belongs to the open interval 1, 2, which is the point given by the Cauchy's mean value theorem. With this exercise also we conclude this lecture for the Cauchy's mean value theorem. Thank you.